Hi, welcome back, and we're going to start our new and final unit for this semester, which is oscillations and waves. So the first chapter here is just oscillations and mainly simple harmonic oscillations. And we're going to focus on the oscillations for a spring mass system, and then a simple pendulum, and then the physical pendulum, and then we'll talk about damped oscillations, and that should bring us to the end of the chapter. Now, oscillatory motion is repetitive motion back and forth around some equilibrium point. The time it takes to do one cycle is called the period, and it's given the symbol capital T. Simple harmonic motion is motion that oscillates, but it's even more specific than that, because the oscillations could be more complicated, but the simplest here will be the simple harmonic oscillations that follow sines or cosines. The amplitude of the oscillation is the maximum disturbance or maximum distance away from equilibrium. And the frequency is simply defined as 1 over the period. So let's get to it. So here is a spring, and I'm going to draw it here. Okay, this is the spring, and it's undisturbed, it's alone, nobody is moving it, nothing is attached to it. That's called the initial position. Now, you come along, you attach a mass to it, and you pull it to the right. Right? Let me call this here x equal to 0, and here the maximum disturbance from equilibrium is the amplitude x equal to a. Here, this is x equal to a. Okay, maximum disturbance from equilibrium. The mass is m. So you pulled it. When you let go, remember when you stretch the spring to the right, it wants to pull you back to the left. So there is a restoring force. So what it does is it will start pulling you and accelerate you until you pass through the equilibrium, and then you overshoot, you go to the other side. So when you get to the equilibrium here, you will have the maximum speed. Why? The reason is the force is in this direction until you get here. Once you pass here, the force switches because the spring starts to become compressed, and then it reverses direction. The force comes this way, but the velocity is this way. Remember, when force and velocity are in opposite directions, it means acceleration and velocity are in opposite directions, so you slow down. So when you get here, you have the maximum speed. And the mass is still attached. Then, the spring starts to compress and compress, but it doesn't compress forever. Eventually, it stops compressing, and it gets to here. The distance from the other side by which it will compress is also equal to a. We will see that. This is x equal to, or negative a, because this is 0. The distance is a. From here to here, it's a. And from here to here, it is a. So here you have maximum displacement. At this point here, you have v is equal to 0. Here, you have v equal to 0. And here, v is maximum. V is equal to V maximum. Okay. Now, the time it takes to go to complete one period, so let's say we started here, we went here, we went here. The next step will be to come back to the natural position, to come back here, or to pass by that point. Then the next step, you overshoot and stretch because you have some velocity this way. Come back all the way here. That's m. Then you come to a stop and then repeat the motion. The time it takes to go from here to here, and then from here to here, and then from here to here, and then back to the initial starting point, that's the period. That's called the period. And so the time, the period, capital T. Is the period. F is the frequency. And it's just 1 over the period. So the period is in seconds, frequency is 1 over seconds, or hertz. Now, in circular motion, we had angular velocity. Here we will have angular frequency called omega, and it will equal to 2 pi over the period, and it is equal to 2 pi times f, and it's in, so this is in 1 over seconds. This one is in radians per second, and this is in seconds. Right? So let's say you pull a mass, it's on a spring, so we wish to understand the motion. So what you can do is, if you write, what's the force on the mass, at any position, at any point? The force on it is negative kx. Let me write down Newton's second law. The net force is equal to the mass times the acceleration. So this is for a mass on a spring. So if x is positive, the force is negative. If x is negative, the force is positive. So we have F is equal to just negative k times x and ma. But the acceleration is the second derivative of position, so it's the second derivative of x with respect to t. And so, the following here, the second derivative of x with respect to t is equal to negative k over m times x. This is called a second order differential equation. It's not like a regular equation, but it's a differential equation because it involves derivatives and some relationship between the function and its derivatives here. So we seek the solution to it will be a function whose second derivative, like you take a function, you take the second derivative of the function, it will give you exactly the same function with a constant in front of it and a minus sign. And we know those functions, and they're called sines and cosines. Because the derivative of the sine gives you the cosine, and the derivative of the cosine gives you the negative sign. So you get back the sine when you take the second derivative of the sine. Same thing for cosine. So the general solution to this, the general solution would be x of t, x as a function of time, will be to some amplitude times the cosine of, here I'm going to call this here omega times t plus phi. This is called the phase, this is the time, and this is omega, and I call it omega because it would be, it's related to the period and so on, and it's related to this k over m. And this is the most general solution. You can put a times the cosine of omega t. Usually phi here is chosen to be 0, usually. The initial conditions give you that. So let's first of all verify that the second derivative of this is something like that. So let's see, dx dt will give me, derivative of cosine is negative sine, so it would be negative a sine of omega t plus t. But you have to take the derivative of the inside by the chain rule, so you get an omega out. And when you take the second derivative, which is to say take the derivative of this, take the derivative once and then twice. So you take the derivative of the sine, you will get the cosine. So you have the a times the cosine of omega t plus phi. And the derivative of the inside gives you an omega, but you have an omega here waiting for it. So that's an omega squared, and don't forget the minus sign. So you get here negative omega squared, but a times the cosine of omega t plus phi is exactly x. So this is x. So what we're saying is, let's write these under each other. Second derivative is equal to this. And this function whose second derivative gives us that, so let's see here, we got that means, let's just compare them. It means these are equal to each other. So omega will equal to, omega squared is k over m, so omega will be the square root of k over m. That means the period, omega is 2 pi over the period, so the period is 2 pi over omega. It means the period would be 2 pi over the square root of k over m, and so the period would be 2 pi the square root of m over k. Okay, when you derive that, it reciprocates. You get that. So that's the solution to the spring, to the mass on a spring problem. And so before I do an example, you can be asked, what is first of all, let me write it this way. So the solution to it was x of t is equal to a times the cosine of omega t plus phi. V of t, what's the velocity at any time? V of t will be derivative of this, and we did this already. It's this, negative omega a sine, negative omega a sine of omega t plus phi. Right? And I want to show you in a moment how to use this to calculate things. So as our first example here, let's take this. You have an air track glider is attached to a spring. The spring is pulled 20 centimeters to the right, and then it's released at time t equal to 0. And it makes 15 oscillations in 10 seconds. So let's see. Let's draw something. So we have a spring attached to a mass attached to a spring. It's pulled to the right. It's pulled to the right by 15 centimeters. So initially, so here is this thing. So this is the equilibrium, but it's stretched to the right. Here is the mass. So this is called the amplitude, and it is 15 centimeters for this problem. It's 0.15. We pulled it to the right. And then we released it at time t equal to 0, and it makes 15 oscillations in 10 seconds. Let me see here. It makes 15 oscillations in 10 seconds. All right? So what is the position as a function of time? First, the position as a function of time, well, first of all, let's find the period. Find capital T. Well, the period is the time it takes to one cycle. So here you make 15 cycles in 10 seconds. So how many cycles do you make? How long does it take to do one cycle? So it will be 10 over 15. So the period would be 10 seconds over 15 cycles. So how long does it take to do just one cycle? Well, divide the two numbers, and you get the period. The period here will be, let's see, we have 10 over 15. That's 0.6667. So 0.6 7 seconds. So find the frequency. Let's just do this example. Find the frequency. Well, the frequency is 1 over the period. So that would be you just reciprocate this, so it would be 1.5 over the period. 15 over 10 hertz. 1 over seconds or hertz. Part C, find omega. Well, omega is 2 pi over the period, or 2 pi f. It's 2 pi over the period, or it's 2 pi times the frequency. And that's 2 pi times this number. So it's 2 pi times this number. So 2 pi times 1.5, so that's 3 pi. 2 pi times, 1.5, that is 3 pi. So that like 9 something, almost 10. 9.5. Okay, so now find the position as a function of time. What is x as a function of time? Well, let's see. I know that this is a spring mass system, so the spring, this as a function of time is a times the cosine of omega t plus phi, or phi. At t equal to 0, x at t equal to 0, x at time t equal to 0 was 0.15, or the amplitude here was just a, was the amplitude. So here I'm going to plug in t equal to 0 and see what I get. I will get a, at t equal to 0, let me just do it this way. At t equal to 0, x is 15 centimeters, or 0.15. And that has to equal to this function here when you plug in 0. So you get a times the cosine of, omega times 0 is 0, so you get phi here. But this is the amplitude here. The maximum displacement from equilibrium is the amplitude. So I get a from the one side that equals to a times something. So it means this thing has to be 1. So cosine of phi is equal to 1, means phi is equal to 0. Because cosine of 0 is 1, or 2 pi, or whatever. So, so it would be, initially, it's equal to 0. So that means x as a function of time is equal to, let's plug in the numbers now. So a is 0.15 times the cosine. Omega is 3 pi, so I put 3 pi times t plus phi, but phi is 0. This one here, 0 to 1. So phi is 0. So that's the position as a function of time. So if I say, what's the position at time t equal to 100 seconds? You plug in 100 seconds here and calculate. Be careful though. This is in radians, so we're assuming here you should be in radian mode. Don't be in degree mode. If you're in degree mode, everything will be wrong. So be in radian mode. So now, what is the velocity as a function of time? Well, velocity is a function of time. It's the derivative of this. So let's take the derivative of this. Derivative of cosine is negative sine, so you get negative the sine of 3 pi t. And then the derivative of the inside will give me a 3 pi out, and 3 pi times 0.45 times 0.15 will give me 0.45 pi. 0.45 pi. Okay, let's rewrite it. So 0.45 pi sine of 3 pi times t. Okay, that's the velocity as a function of time. The next question would be, for example, the same assumptions. At what time will x equal to half a? So, at what time, or the first time, so you pull the mass to the right here, and then you let go. It's at a, but at some point it will be at half a. How long will it take it to go from here to half a? How much time will it take? Well, let's see. We have x is a function of time equal to the amplitude times the cosine of omega t. Phi is 0. Phi is 0. I will just leave it in general. A A is 0.15 for our problem, omega is 3 pi for our problem, but I will just leave it like that. So I want, when I plug in a certain time, on the left side I get half of the amplitude. So when is this equal to half of the amplitude? Well, I'll plug in half of A here and then solve for the time. So I want x of t equal to 1/2 of A. 1/2 of the amplitude. So I have A, cosine of omega t equals to A. So cosine omega t equals to 1/2. So that means that cosine omega t equal to 1/2. Well, the cosine of something equal to 1/2. What is that something? Cosine of 30, sine of 30 degrees is 1/2. Cosine of 60 is 1/2. 60 is pi over 3. So that means the inside here, the cosine of this thing should be pi over 3. That means omega times t equal to pi over 3. Okay, pi over 3. And so t, since I want in terms of the period here, let me just see here. Omega is 2 pi over the period. It's 2 pi over the period times t equals to pi over 3. Cancel pi on both sides, and you get t would equal to what? Would be t over 6, the period over 6, yeah, would be capital T divided by 6. So it's 1/6 of a period to get from the maximum to half. So since the period here is 0.6666, and so 1/6 of that would be 0.11111. That's how long it will take. Okay. And by the way, when we solve this differential equation here, when you solve the differential equation, we said this is the general solution. Now, how do I know that this is the only solution? There is a theorem. There is always, whenever you solve differential equations, first of all, it's mostly guesswork. You have to guess the solution, and then if it satisfies the differential equation with the initial conditions, then it is the solution. It is unique. There is always this question about existence and uniqueness. Does the solution exist? Is there a solution? And if yes, if there is a solution, is it unique? That's always a question. So here, it turns out for well-behaving functions, if the solution here satisfies the differential equation with the initial condition satisfied, then that is the solution. That is the only solution. It is the unique solution. I would like to just quickly talk about conservation of energy in simple harmonic motion. For example, for this mass on a spring. So we said for x of t, it's equal to, in general, it's a times the cosine of omega t plus some function here. And then v of t, you take the derivative of this with respect to time, so you get negative a omega times the sine of omega t plus v, right? Now the elastic potential energy is 1/2 kx squared, so you get 1/2 kx squared. The velocity here, since that's the velocity, then the kinetic energy is 1/2 mv squared, 1/2 mv squared. So let's see. So here I have 1/2 k. Let's square this. When you square this, you just get a squared cosine squared. A squared times the cosine squared of omega t plus v. And when you square this, you get 1/2 m, and let's square this. You square the minus sign, it goes away, so you just get a squared omega squared. A squared omega squared sine of omega t plus phi. But what's the relationship between k and omega and m? Omega squared is k over m. Omega squared is k over m. So remember, recall. So the total energy, the total mechanical energy is x as a function of time. No, I'm sorry. It would be the potential energy plus the kinetic energy. It will be this. It will be 1/2 kx squared plus 1/2 mv squared. Now, when x is maximum, when let's say if you have a spring and it's as far away from equilibrium as possible, the velocity then is 0. So when the potential energy is maximum, the kinetic energy is minimum, but their sum is always E. It's constant. This is constant. There are no non-conservative forces involved in this problem so far. So for example, I could calculate the total energy by just asking when is x maximum? That's the amplitude, so it's 1/2 ka squared. And this part will be 0. Or I can also say, I will calculate it when V is maximum, when it passes through the equilibrium point, when the spring is neither stretched nor compressed, so x is 0. So this part will be 0, but this one will be V maximum. So it's 1/2 of m V maximum squared. But what is V maximum? What's the maximum speed? Maximum speed is, the sine is a function that oscillates between +1 and -1. So the speed is maximum and this is either plus or -1. So the maximum speed is just the front here. That's the maximum. It's a omega. So it would be 1/2 m a squared omega squared. And these two are supposed to be equal to each other. They're supposed to be equal to each other. And they are. They are because it is, so I have this here, 1/2 m a squared times omega squared, but omega squared, I made a mistake here. Omega is equal to the square root of k over m. Omega squared is just k over m. So instead of omega squared, I will write k over m. So the m cancels and you have 1/2 ka squared. So the energy, it is 1/2 ka squared. It's just a different way to write it. And but then how do I know? So the energy when the position is maximum or when the velocity is maximum, it's equal. But how do I know that, how do I make sure that this is always constant? How do I prove that? Because it seems like this depends on time and this depends on time, and somehow they have to add up to a constant. It turns out not to be very difficult, because let's just add them. Add this and add this to get the total energy. So let's add them. You get 1/2 ka squared cosine squared of omega times t plus phi plus 1/2 m a squared omega squared, but m a squared omega squared is ka squared. It's just the same as ka squared. So it's 1/2 ka squared times the sine. I forget to square the sine here. So sine squared of omega t plus phi. And if you factor the 1/2 k, one more typo, 1/2 this. So I have, when you factor the 1/2 ka squared out, you will get the cosine squared of omega t plus phi plus the sine squared of omega t plus phi. And sine squared plus cosine squared of that same angle, you get 1. So it is constant, 1/2 ka squared. The amplitude is whatever it is, it's a constant value. And by the way, if you graph this velocity here, it will look like this. It's a negative sign function. T, this is V, it's a negative sign, looks like this. And this part here is the negative a omega, and this here would be positive a omega. But the magnitude of the maximum velocity is a omega, simply a omega. All right, I'll pause this one here and we'll continue in the next video.